In a three-wire delta system, the three phases A, B, and C are connected in a triangular configuration. In an ungrounded delta system, none of the phases are connected to ground. The main concern with ungrounded delta systems is the potential for capacitive coupling. Capacitive coupling occurs when an ungrounded conductor is exposed to a live conductor. Over time, the insulation between the two conductors can degrade, allowing current to flow between them. In an ungrounded delta system, the exposed conductor, usually phase B, can become capacitively coupled to the other two phases, A and C. This can result in line voltage, typically 230 volts or 480 volts, appearing on phase B, even though it is labeled as grounded. Capacitive coupling on an ungrounded delta system can create a hazardous situation. If a person touches phase B while it is capacitively coupled, they can experience an electrical shock. Additionally, the presence of line voltage on phase B can damage connected equipment. Grounding phase B eliminates capacitive coupling, reducing the risk of electrical shock and equipment damage. If consideration is being given to disconnecting grounded phase B in delta systems, it is essential to carefully assess the risks involved. The following factors should be considered. Firstly, condition of the insulation. The degradation of insulation over time is what allows for capacitive coupling. If the insulation is in good condition, the risk of capacitive coupling is reduced. Secondly, environment. The presence of moisture and contaminants can accelerate the degradation of insulation. Systems in humid or corrosive environments may be more susceptible to capacitive coupling. Thirdly, adequacy of other grounding measures. If the delta system is part of a larger electrical distribution network, other grounding measures such as grounding the transformer neutral may provide sufficient protection against capacitive coupling. Fourthly, cost-benefit analysis. The cost of disconnecting grounded phase B must be weighed against the potential risks of leaving it grounded. It is recommended that a qualified electrical engineer be consulted to assess the risks and make an informed decision about whether or not to disconnect grounded phase B in three-wire delta systems. In more detail, let's explore the concept of ungrounded three-wire delta systems and why grounding one phase, typically phase B, is often implemented for safety. We will delve into the phenomenon of capacitive coupling, its implications, and the factors to consider when deciding whether to maintain or disconnect a grounded phase in such systems. An ungrounded three-wire delta system consists of three phases, labeled A, B, and C, connected in a closed loop, forming a triangular configuration. Unlike grounded systems where one point, usually the neutral, is connected to ground, an ungrounded delta system has no direct connection to Earth. This lack of a ground reference introduces unique characteristics and potential hazards. One of the primary concerns with ungrounded delta systems is the phenomenon of capacitive coupling. Capacitive coupling occurs when an ungrounded conductor is in close proximity to another conductor, creating a capacitor-like effect. The insulation between the conductors acts as a dielectric, and an electric field is established between them. Over time, the insulation can degrade due to factors such as heat, moisture, and contaminants. As the insulation weakens, the capacitive coupling increases, allowing current to flow between the conductors. In an ungrounded delta system, phase B, which is often designated as the grounded phase, can become capacitively coupled to the other two phases, A and C. This coupling can result in a voltage appearing on phase B, even though it is supposed to be at ground potential. The magnitude of this voltage depends on several factors, including the condition of the insulation, the distance between the conductors, and the frequency of the system. The presence of voltage on phase B due to capacitive coupling can create safety hazards. If a worker comes into contact with phase B while it is capacitively coupled, they may experience an electric shock. The severity of the shock depends on the voltage level and the individual's resistance. Additionally, the voltage on phase B can damage connected equipment. Electronic devices and other sensitive equipment may not be designed to withstand the voltage fluctuations caused by capacitive coupling. The decision to ground phase B in a delta system is often driven by the need to mitigate these safety concerns. By grounding phase B, the capacitive coupling is effectively eliminated. The ground connection provides a path for the induced current to flow back to the source, preventing the buildup of voltage on phase B. This reduces the risk of electric shock and equipment damage. However, disconnecting grounded phase B is a complex issue that requires careful consideration. Several factors must be evaluated before making a decision. The first factor to consider is the condition of the insulation. If the insulation is in good condition, the risk of capacitive coupling is reduced. However, if the insulation is old, damaged, or contaminated, the risk increases significantly. A thorough inspection of the insulation is necessary to assess its condition. The second factor to consider is the environment. Humid or corrosive environments can accelerate the degradation of insulation. If the system is located in such an environment, the risk of capacitive coupling is higher. Protective measures, such as sealing the conductors or using corrosion-resistant materials, may be necessary. The third factor to consider is the adequacy of other grounding measures. If the delta system is part of a larger electrical distribution network, other grounding measures may provide sufficient protection against capacitive coupling. For example, grounding the transformer neutral can help to stabilize the voltage and reduce the risk of voltage fluctuations. The fourth factor to consider is the cost-benefit analysis. Disconnecting grounded phase B may offer some benefits, such as improved system reliability or reduced maintenance costs. However, these benefits must be weighed against the potential risks of leaving it ungrounded. A comprehensive cost-benefit analysis should be conducted to determine the most appropriate course of action. In summary, ungrounded three-wire delta systems present unique challenges and potential hazards. Capacitive coupling can lead to voltage buildup on phase B, creating a risk of electric shock and equipment damage. Grounding phase B is a common practice to mitigate these risks. However, disconnecting grounded phase B requires careful consideration of factors such as insulation condition, environment, grounding measures, and cost-benefit analysis. It is highly recommended to consult with a qualified electrical engineer to assess the risks and make an informed decision. Further elaborating on the nuances of ungrounded three-wire delta systems, the characteristics, and the crucial considerations for grounding, let's explore in greater detail the underlying principles and practical implications. Unlike grounded systems that provide a direct, low-impedance path for fault currents to return to the source, ungrounded delta systems lack this direct connection to Earth. This absence of a ground reference leads to distinct operational characteristics, including a higher susceptibility to transient overvoltages and the aforementioned capacitive coupling. Capacitive coupling, as previously discussed, arises from the inherent capacitance between conductors, particularly in close proximity and separated by insulation. This capacitance forms a pathway for alternating current to flow, even when the conductors are not directly connected. In an ungrounded delta system, the capacitance between each phase conductor and ground creates a balanced capacitive network. However, any imbalance in this network, such as a degradation of insulation on one phase or the presence of a nearby grounded object, can lead to voltage imbalances and the appearance of voltage on the supposedly grounded phase B. The magnitude of this voltage depends on the degree of imbalance and the system voltage. The consequences of capacitive coupling extend beyond potential electric shock hazards. The presence of unexpected voltage on phase B can disrupt the operation of sensitive electronic equipment, causing malfunctions or even damage. It can also complicate troubleshooting efforts, as technicians may mistakenly assume that phase B is a ground potential when it is not. To mitigate these risks, grounding phase B is a common practice in grounded delta systems. Grounding provides a low impedance path for fault currents to flow back to the source, effectively neutralizing the capacitive coupling and preventing the buildup of voltage on phase B. This not only enhances safety but also improves the reliability and stability of the system. However, the decision to ground phase B is not without its trade-offs. Grounding introduces a new set of considerations, such as the potential for ground faults and the need for ground fault protection devices. A ground fault occurs when a phase conductor comes into contact with ground, creating a high current flow. In a grounded delta system, a ground fault can quickly escalate and cause significant damage if not properly detected and cleared. Therefore, it is essential to install ground fault protection devices, such as ground fault circuit interrupters, to detect and interrupt ground faults before they can cause harm. Another consideration is the impact of grounding on system coordination. System coordination refers to the selective tripping of circuit breakers or fuses to isolate a fault while minimizing the disruption to the rest of the system. In a grounded delta system, ground faults can affect system coordination, as they can cause multiple breakers to trip simultaneously. Careful planning and coordination are necessary to ensure that the system operates safely and reliably. Now, let's delve into the specific factors that should be considered when deciding whether to disconnect grounded phase B. As mentioned earlier, the condition of the insulation is paramount. If the insulation is old, damaged, or contaminated, the risk of capacitive coupling is significantly higher. In such cases, it may be prudent to maintain the grounded phase B to provide an additional layer of protection. However, if the insulation is in good condition and the system is well maintained, the risk of capacitive coupling may be lower. In this scenario, disconnecting grounded phase B may be a viable option, provided that other safety measures are in place. The environment in which the system operates also plays a crucial role. Humid or corrosive environments can accelerate the degradation of insulation, increasing the risk of capacitive coupling. In such environments, it is generally advisable to maintain grounded phase B. However, in dry and clean environments, the risk may be lower, and disconnecting grounded phase B may be considered. The adequacy of other grounding measures is another important factor. If the delta system is part of a larger electrical distribution network, other grounding measures may provide sufficient protection against capacitive coupling. For example, grounding the transformer neutral or using a high resistance grounding system can help to stabilize the voltage and reduce the risk of voltage fluctuations. In these cases, disconnecting grounded phase B may be feasible as long as the other grounding measures are properly implemented and maintained. Finally, a comprehensive cost-benefit analysis should be conducted to weigh the potential benefits of disconnecting grounded phase B against the potential risks. The benefits may include improved system reliability, reduced maintenance costs, or enhanced system performance. However, the risks may include increased risk of electric shock, equipment damage, or system instability. A careful evaluation of these factors is essential to make an informed decision. In conclusion, ungrounded three-wire delta systems present unique challenges and require careful consideration of grounding practices. Grounding phase B is a common practice to mitigate the risks of capacitive coupling and enhance safety. However, disconnecting grounded phase B is a complex decision that requires careful evaluation of insulation condition, environment, other grounding measures, and cost-benefit analysis. Consulting with a qualified electrical engineer is highly recommended to assess the risks and make an informed decision. Continuing our comprehensive exploration of ungrounded three-wire delta systems, it is crucial to delve deeper into the practical aspects of assessing insulation condition, understanding the nuances of environmental factors, and evaluating alternative grounding methodologies. Furthermore, a rigorous cost-benefit analysis should incorporate long-term operational considerations. Let's begin with the assessment of insulation condition. Visual inspection is a fundamental first step. Look for signs of cracking, discoloration, or physical damage to the insulation. These visual cues can indicate potential weaknesses in the insulation's ability to withstand voltage stresses. Infrared thermography can be employed to detect hotspots on the insulation surface. Elevated temperatures can indicate areas where the insulation is breaking down, leading to increased current leakage and a higher risk of capacitive coupling. Insulation resistance testing, often performed with a megometer, measures the resistance of the insulation to the flow of direct current. A low insulation resistance value suggests that the insulation is compromised and may be susceptible to capacitive coupling. Dielectric strength testing involves applying a high voltage to the insulation and measuring the current that flows through it. This test can reveal hidden weaknesses in the insulation that may not be apparent through visual inspection or insulation resistance testing. Polarization index testing measures the ratio of insulation resistance after 10 minutes to the insulation resistance after 1 minute. A low polarization index indicates that the insulation is contaminated or has absorbed moisture, increasing the risk of capacitive coupling. Now, let's examine the environmental factors that can influence insulation performance. High humidity levels can significantly reduce the insulation resistance and increase the risk of capacitive coupling. Moisture can penetrate the insulation, creating conductive pathways and facilitating current leakage. Corrosive environments, such as those containing salt spray or industrial pollutants, can accelerate the degradation of insulation. Corrosive substances can attack the insulation material, weakening its structure and reducing its dielectric strength. Extreme temperatures, both high and low, can also affect insulation performance. High temperatures can cause the insulation to dry out and become brittle, while low temperatures can make it more susceptible to cracking. Ultraviolet radiation from sunlight can also degrade insulation over time, causing it to become discolored and less flexible. Vibration and mechanical stress can also contribute to insulation failure. Constant vibration can weaken the insulation material, while mechanical stress can cause it to crack or break. Next, let's evaluate alternative grounding methodologies that can be employed in conjunction with or as a substitute for grounding phase B. High resistance grounding utilizes a resistor connected between the neutral point of the transformer and ground. This limits the ground fault current to a low level, reducing the risk of damage to equipment and improving system coordination. Low resistance grounding employs a lower value resistor compared to high resistance grounding, allowing for a high ground fault current. This provides better protection for equipment but may require more careful system coordination. Solidly grounded systems connect the neutral point of the transformer directly to ground. This provides a low impedance path for ground fault currents, but it can also lead to high fault currents and potential equipment damage. Ungrounded systems, as previously discussed, do not have a direct connection to ground. This can reduce the risk of ground faults but increase the risk of capacitive coupling and transient overvoltages. Zigzag transformers can be used to create a grounded neutral point in an ungrounded delta system. This provides a low impedance path for ground fault currents without requiring a direct connection to ground. Finally, let's consider the long-term operational considerations that should be included in a cost-benefit analysis. Maintenance costs associated with grounded and ungrounded systems should be carefully evaluated. Grounded systems may require more frequent maintenance due to the potential for ground faults, while ungrounded systems may require more frequent insulation testing to detect capacitive coupling. Downtime costs associated with system failure should also be taken into account. Grounded systems may experience more frequent but shorter outages due to ground faults, while ungrounded systems may experience less frequent but longer outages due to insulation failures. Equipment replacement costs should also be considered. Grounded systems may require more frequent replacement of equipment due to damage from ground faults, while ungrounded systems may require more frequent replacement of insulation due to degradation from capacitive coupling. Safety risks and associated costs should also be factored into the analysis. Grounded systems may have a lower risk of electric shock due to capacitive coupling, but they may have a higher risk of arc flash incidents due to ground faults. Insurance premiums may also be affected by the choice of grounding methodology. Insurance companies may charge higher premiums for systems that are deemed to be less safe. In conclusion, the decision to disconnect grounded phase B in an ungrounded 3-wire delta system is a complex one that requires a thorough understanding of the underlying principles, practical considerations, and long-term operational implications. A comprehensive assessment of insulation condition, environmental factors, alternative grounding methodologies, and long-term costs is essential to make an informed decision. Consulting with a qualified electrical engineer is highly recommended to ensure that the system is designed and operated safely and reliably. Building upon our extensive discussion of ungrounded 3-wired delta systems, let's further examine the application of advanced diagnostic techniques for assessing insulation health, the implementation of mitigation strategies for capacitive coupling, and the critical role of protective devices in ensuring system safety. We will also delve into the evolving standards and best practices that guide the design and operation of these systems. To begin, let's explore advanced diagnostic techniques for assessing insulation health. Partial discharge testing is a non-destructive technique that detects the presence of small electrical discharges within the insulation. These discharges can indicate areas where the insulation is breaking down and may eventually lead to failure. Frequency domain spectroscopy measures the impedance of the insulation over a range of frequencies. This technique can provide valuable information about the insulation's dielectric properties and can help to detect early signs of degradation. Time domain reflectometry sends a pulse of energy down the conductor and measures the reflections that occur. This technique can be used to locate faults and other discontinuities in the insulation. Ultrasonic testing uses high-frequency sound waves to detect flaws and defects in the insulation. This technique can be particularly useful for inspecting insulation that is inaccessible or difficult to visually inspect. Chemical analysis of insulation samples can provide valuable information about the insulation's composition and condition. This technique can be used to detect the presence of contaminants, moisture, or other degradation products. Next, let's examine mitigation strategies for capacitive coupling in ungrounded delta systems. Shielding conductors can reduce the capacitive coupling between conductors by providing a grounded barrier. The shield intercepts the electric field and prevents it from coupling to other conductors. Using twisted pair conductors can also reduce capacitive coupling. The twisting of the conductors cancels out the electric field and minimizes the capacitance between them. Increasing the spacing between conductors can also reduce capacitive coupling. The capacitance between conductors decreases as the distance between them increases. Applying a conformal coating to the insulation can protect it from moisture and contaminants, reducing the risk of degradation and capacitive coupling. Implementing a regular insulation testing program can help to detect early signs of degradation and capacitive coupling, allowing for timely repairs and preventative maintenance. Now, let's discuss the critical role of protective devices in ensuring system safety in ungrounded delta systems. Ground fault circuit interrupters, as previously mentioned, are essential for detecting and interrupting ground faults. These devices can quickly detect even small ground faults and trip the circuit, preventing electric shock and equipment damage. Surge protective devices can protect equipment from transient overvoltages caused by lightning strikes or switching surges. These devices divert the surge current to ground, preventing it from damaging sensitive equipment. Overcurrent protection devices, such as circuit breakers and fuses, protect the system from overloads and short circuits. These devices trip the circuit when the current exceeds a predetermined level, preventing damage to conductors and equipment. Voltage monitoring devices can continuously monitor the system voltage and detect voltage imbalances caused by capacitive coupling or other factors. These devices can trigger an alarm or trip the circuit if the voltage exceeds a predetermined level. Finally, let's consider the evolving standards and best practices that guide the design and operation of ungrounded delta systems. The National Electrical Code provides comprehensive guidelines for the safe installation and operation of electrical systems, including ungrounded delta systems. The Institute of Electrical and Electronics Engineers develops standards for electrical equipment and systems, including standards for grounding and surge protection. The International Electrotechnical Commission publishes international standards for electrical safety and performance. Industry best practices, such as those developed by the Electrical Safety Foundation International, provide guidance on safe work practices and preventative maintenance for electrical systems. Continuing education and training are essential for electrical professionals to stay up to date on the latest standards, best practices, and technologies related to ungrounded delta systems. In conclusion, the safe and reliable operation of ungrounded three-wire delta systems requires a comprehensive approach that incorporates advanced diagnostic techniques, effective mitigation strategies, robust protective devices, and adherence to evolving standards and best practices. The electrical professionals must remain vigilant and proactive in their efforts to ensure the safety and performance of these systems.